So for this talk, I was asked to, talk about some very recent results about zero knowledge, and naturally I chose one of my papers. The talk is titled Fiat-Shamir from Practice to Theory. It's kind of a talk about really a line of a few works really from recent years. So this is kind of all very brand new. About the title, as Benny said, it's half joke but half serious. Usually we're more interested in moving from theory to practice. Some of Fiat-Shamir has been, I would say, very successful in practice. And theory land, we mainly knew negative results. And here in this kind of line of works, we're trying to import some of the success of Fiat-Shamir in practice and be able to say positive things also theoretically. And we'll see more in the talk. So I should say that this talk is based on a sequence of joint works with Ron Canetti, Lei Chen, Justin Holmgren, Yael Kalai, Alex Lombardi, Leah Raisin, and Guy Rothblum. Okay, so let's start. So brief reminder about stuff we saw in the morning. What is the Fiat-Shamir transform? It's a generic way to take an interactive protocol, public coin protocol, and transform it, squish out all the interaction, and get something, a new protocol relative to a hash function, which consists of a single message sent from the verifier to the prover. And the transforms looks like this if you missed the morning session. And we raised this question of whether this transform is secure. And we saw the result of Poincheval and Stearns that it is secure in the random oracle model when we're using a hash function that is a fully random function. And, this gives some indication. But what can we say about explicit hash families? And we started talking about this in the previous in the morning session. We're going to go into more detail now. And again, just to recap a few of the definitions that we said. First of all, we're going to say that a hash function family H is Fiat-Shamir or FS compatible for a protocol pi if after compiling the protocol in the way that we saw using Fiat-Shamir and the hash function family H, what we get is a sound argument system. And in contrast to the previous talk, I'm focusing here mainly on soundness and not on zero knowledge. And the reason is that we saw that kind of just this notion of programmability, which turns out we can often get, suffices for zero knowledge. So the focus of the talk is on soundness. Okay, so for this talk, we're saying that the hash function is Fiat-Shamir compatible if the resulting argument is sound. I don't have a timer, so I'll use this. Okay. A theorem or result that I mentioned and Alon essentially showed you is the protocol of Barak and the follow-up of Goldwasser and Kalai is a protocol which is not Fiat-Shamir compatible. So it's a single protocol that is incompatible with any hash function family. Okay, so strong negative result. But we said that the ray of hope that we have is that these counterexamples happen to be arguments, meaning that the soundness guarantee is only computational. Maybe we can hope for better if our starting point is a stronger notion of soundness, statistical soundness. So the interactive protocol that we start off with, we want to assume that it has soundness against computationally unbounded cheating provers, even those that run an exponential time, break cryptography, solve NP-complete problems, and so forth. So that's our starting point. We start with that kind of protocol. We compile with Fiat-Shamir. So an interactive proof and apply Fiat-Shamir. Is the resulting thing sound? And also here we have this negative indication, a result of Vitansky et al., showing that there are no black box reductions, whatever that means, a falsifiable assumption, even for proofs. What this says, I don't want to define everything here. The point is that it seems the moral of these results, or I think the way they were interpreted at the time, is that standard techniques and standard assumptions won't be able to show that Fiat-Shamir works for proofs in a generic way. And this, I viewed at the time as a negative indication. I think many others did as well. Nevertheless, in this talk, what I want to show you is some positive results about constructions of hash function families that are Fiat-Shamir compatible when you start off with an interactive proof. And you may wonder, how does this play with the impossibility or the barrier that we just mentioned of Vitansky et al. And the way that we bypass their impossibility results is essentially in two ways. First, for the results that I'm going to talk about today, we're going to be using quite strong assumptions, which they don't cover, so not standard assumptions as we'd like. Also, a different way in which we bypass, and there have been follow-up works that I will mention, and even go further with that, is by, instead of considering all interactive proofs, focus on some particular interactive proofs that are actually, in some sense, the most interesting ones. So not a general result for all interactive proofs, but only for the ones that we care about, or for some of the ones that we care about. So let me mention this pretty amazing sequence of follow-up works after the results that I'll talk about from, this one is ancient history. It's from January. This one's from February. So just last week, we had this really remarkable result of Pikert and Seehan. I hope I'm pronouncing his name correctly, which shows non-interactive zero knowledge from LWE, long-standing and important open question in cryptography. And the way that it is done is essentially by implementing the Fiat-Shamir for a particular Fiat-Shamir transform for a particular interactive proof using a hash function that they construct based on the hardness of LWE, learning with errors. Second very interesting result I forgot the authors, but Alon and the co-authors, using the Fiat-Shamir transform to show actually hardness of p-pad, so showing hardness of finding a Nash equilibrium. So pretty striking sequence of follow-up works also. Okay, but I want to focus on not on those results, on some of the things from ancient history from 2018. And I want to warn you that, I'm going to be listing some very strong assumptions, so I want to be totally upfront about it. The point is that these assumptions give us what I think are meaningful and interesting results. And beyond that, I think they've had a part in these follow-up works which use much weaker assumptions. Okay. So before stating what our results are, I want to talk about a notion that I'm going to call optimal hardness. As I said, it's going to be a very strong assumption, but it's a clean one. And so let's see what it means. So generally speaking, when I say a cryptographic primitive is optimally hard, I mean that if you look at a polynomial time adversary that's trying to break the assumption, whatever the assumption may be, so optimal hardness means that a polynomial time adversary can only succeed in breaking the assumption with probability that is kind of trivial. So poly lambda over 2 to the lambda. So if you think of say the task of inverting a one-way function or a one-way permutation, I'm giving you y and I'm asking you to find x. Clearly you can, and you're allowed to run in polynomial time. Clearly one thing that you can do is just sample random a polynomial number of elements in the domain and check whether they are valid preimages of your y. Your success probability will be poly lambda over 2 to the lambda. And this very strong assumption that I want to make, optimal hardness of a one-way function, is that you cannot do better than that. So you cannot do any, this inversion with probability that is more than polynomially better than the trivial attack. And indeed, this is a very strong security requirement. I want to contrast this notion, and I want to emphasize that what I'm talking here about is the probability of success rather than the running time of the adversary. So there are some relations, but and then I'll say what the relations are in a second. But notice that if I were to assume, say, that a one-way function or one-way permutation is hard for an adversary running in time to the lambda over poly lambda, that would be flat out false. So here, whereas this style of assumption, when we're talking about the success probability, is conceivable, and in particular, a random oracle will have this property, even though the point is to avoid random oracles, but just as a sanity check. It's possible to have such functions. Moreover, so again, talking about this relation of time versus success probability, when you're talking about a cryptographic primitive in which the challenge is re-randomizable, then this notion of optimality in terms of probability is weaker than optimal slice hardness because you can just repeat. If you have something that works with non-trivial success probability, you can just repeat it again and again and again by re-randomizing your challenge and hope, and in longer time, you're going to succeed, but with high probability. It also says something interesting about the cryptographic primitive in the sense that you have a polynomial space attack. So if you have a break of optimal hardness in this notion, you get a polynomial space attack, which, non-trivial polynomial space attack, which I think is also interesting. So it's an indication that this notion is, in my view, is non-trivial and interesting. Okay, so that was optimal hardness. I need this notion in order to state what our results are, talking about Fiat-Shamir for proofs. And I will actually list three different results, which are in spirit, so not formally, but in spirit, they're improvements. In order. I'm not telling you just the last one because I think for two reasons. One, I kind of want to show you how, even though we're using very strong assumptions, the assumptions, in my mind, have dramatically improved, even though they're still very strong. And second, when I show you some of the ideas that go into the proof, I'm going to start off, somewhere in the middle here. Okay, so kind of the first positive indication at all of being able to do Fiat-Shamir for interactive proofs was in a joint paper with Yael Kalai and Guy Rothblum, where what we showed is under, again, super duper strong assumptions that this is possible. The assumptions were, so sub-exponential indistinguishability obfuscation. For those who are not familiar, it's talking about code obfuscation. It's safe to say that this is a very strong assumption. On top of that, we also need something that's called optimal input hiding obfuscation. So the flavor of obfuscation here is weaker than this indistinguishability obfuscation, but we're talking about optimal hardness. So both the sub-exponential I/O and optimal input hiding obfuscation, each one of these is an extremely strong assumption. Nevertheless, this was the first feasibility result. In follow-up work with Canetti, Chen, and Raisin, we showed a related result. The way it's stated here, it's not clear what the relation is, but it actually is quite related. So what we showed is that if you have an optimal KDM secure encryption scheme, okay, so what is KDM? KDM stands for key-dependent messages. It's basically encryption schemes in which you want security to hold, even if the messages that you're encrypting are themselves functions of the secret key. Okay, and we're going to see a definition, pretty formal definition in a few slides, but this is talking about kind of key-dependent secure encryption. And so not only are we talking about optimal hardness of such encryption schemes, also the type of key functions of the key that I allow the adversary to see can be unbounded functions. Okay, so it's not, you maybe would have, like the most naive thing you would have thought of is that, I take the key K and encrypt K using K both as the key and the message. So that's kind of a basic form of key-dependent security. Here I'm saying I give the adversary an arbitrary function, so encryption using key K of f of K, where f can be some computationally unbounded function. So very strong assumption, in particular to those in the audience who are familiar with the term, it's not a falsifiable assumption. Nevertheless, it is an improvement over what we had here, morally if not formally. And in the most recent work from last year, which will appear actually this year, we managed to get rid of this assumption on the key-dependent message being computationally unbounded, which is what was the main component in what made our assumption not be falsifiable. So we only need functions of the key that are efficiently computable. But now we can only argue soundness not for any interactive proof, but only for a nice interactive proof. Okay? So now comes the question of what is a nice interactive proof, and we're going to see that shortly. But suffice to say for now that the most important bit is that interactive proofs that we care about happen to be nice. So this is a meaningful statement. Okay, but again, you see here how we leverage the fact that we're looking at subclasses of interactive proofs to improve our assumptions. Okay, questions so far? So it depends. I will talk, so for some of the results I will have an a priori bound, for some I will want any large polynomial. And, right, but I want optimal hardness. Right, but I'm going to talk about it. And also without an a priori bound, we have such schemes, but again, not with optimal hardness using FHE. Okay, so that's kind of how we get Fiat-Shamir for proofs. As we said, Fiat-Shamir is a useful thing, so we can derive some corollaries or some applications. So let me mention them, and we'll talk about them more throughout the talk. So one corollary is that we were able to construct non-interactive argument systems. Here, I guess we can probably get zero knowledge on top, but we didn't try really hard. Our focus was really on soundness. So we can get very efficient non-interactive arguments for NC. NC is the class of all kind of low-depth computations. And this is under the assumption that certain suitable fully homomorphic encryption schemes are optimally hard for key recovery. We'll see it more precisely in a second. The key thing that I skipped over is that these schemes are publicly verifiable, meaning that it's non-interactive. So we can kind of post the first message, which is the verifier message, globally. You can think of it as a CRS, and now prove statements. And the CRS is also very short. Oops. The second result that I want to mention is that using kind of a weaker assumption, that search LWE is optimally hard, meaning if you want to solve search LWE, you can only do this with exponentially small success probability. We obtain NIZKs for all of NP. This result is essentially superseded by this beautiful work by Picard and Sehan, which obtain NIZK for just vanilla LWE. Right, we can get statistical zero knowledge, uniform CRS, or curse, what I called yesterday, common uniform random string, and adaptive soundness. And the corollary that we get via the work of Dvork, Naor, Reingold, and Stuckmeyer is something that Alon mentioned, which is that, say, parallel repetition of the quadratic residuosity zero knowledge protocol, or the first zero knowledge protocol that we had from the work of GMR. If you take parallel repetition of that, that will not preserve zero knowledge. And that, again, I guess both of those so both the second and third results stated here are now superseded by the work of Picard. So we can get this only assuming LWE, which I think is pretty remarkable. Okay, so I want to tell you a little bit about what goes into the proof of these statements. And again, stop me at any time if you have questions. Okay, so I'm going to skip over the first result and start here. And that will be kind of motivation to skip also to tell you about the third result. So I'm going to start off by telling you what I mean more precisely about this optimal KDM for unbounded KDM functions. So here's the assumption. So we're going to talk about symmetric key encryption, it's good actually. So kind of simpler notion. And I want to assume optimal KDM hardness for key recovery. So what does this mean? So take any polynomial time adversary A. Now I give A an encryption under key K of f of k. So I'm giving the adversary an encryption of some function, some incredibly complex function of the key, and I'm asking the adversary now to fully recover the key. And the requirement is that the adversary can kind of do no better than guessing, roughly speaking. Okay, so probability at most poly lambda over 2 to the lambda, and this should hold for any function f. Okay, even the ones that are not efficiently computable. Indeed, a very strong assumption. The second property that I want to require, which is, I think of it as a statistical property or about the structure of the encryption scheme rather than a security property, is something that we call universal ciphertext, which says, so actually don't look at what the slide says. I think a better way of phrasing it would be that for any two fixed keys, if you look at the distribution that you get with key number 1 encrypting a random message versus key number 2 encrypting a random message, you get the same distributions. In particular, this means that ciphertexts are not attached to any one particular key. Any ciphertext is decryptable under all keys. Okay, and it turns out just this part of the assumption is something that you can get fairly easily from known encryption schemes. Okay, and I think of it as a statistical property, not as or structural property, not a security property. Okay, so how do we use these assumptions? So actually, before telling you how we use them, I want to define a central notion for the rest of the talk. And in general, I think it's a key notion and really interesting. It's called correlation intractability, defined by Canetti, Halevi, and Goldreich in, I guess, 04 is the journal version. So it's a property of hash functions. They say that a hash function, H, is correlation intractable for a relation R. We're going to be looking at sparse relation. Sparse relation means that for every X, there are very few Y's in the relation. And the property says that if I give you a random hash function from this family, it's going to be very difficult for you to find X, so that X comma H of X is in the relation. Okay, so say the relation can be, let's say, so like simplest relation, I think it's what Bitcoin uses, is, so XY is in the relation if Y is, say, has a prefix of a bunch of zeros. Okay, and the relation kind of doesn't care about X, then this relation is indeed sparse, and it's asking, given H, can you find X such that H of X has a prefix of zeros? Okay, that's kind of a simple relation that we want to handle. The definition talks about, a general relation. Right, so to put it in a slightly more formal way, what we're asking is that for any polynomial time adversary, if I sample a random hash function from the collection, I give the adversary a description of the hash function and ask the adversary to give me back X, the probability that X comma H of X is in the relation is negligible. So that's correlation intractability. And why did I bring this notion up? Well, it turns out that it's kind of intimately related to the soundness of Fiat-Shamir when applied to interactive proofs. Why? Well, so rather I claim that if you're using a correlation intractable hash function family to instantiate Fiat-Shamir for proofs, you're golden. So let's see this. And let's focus on the case of 3 message protocols. Right, so on the left, I have a protocol, as we saw in the morning, alpha, beta, gamma. Right, alpha and gamma being sent from the prover, beta sent from the verifier, just random coin tosses. And we're compiling it using Fiat-Shamir with a correlation intractable hash function as follows. So our verifier chooses a hash function from the collection, sends it over to the prover. Prover generates alpha as here. The honest prover generates alpha as here, computes beta as the hash of alpha and X, generates gamma and sends over alpha and gamma. You can send over also beta if you would like to. Doesn't matter. And I claim that if the hash function family is correlation intractable for a suitable relation, then this will be sound. Why? So think about the following relation. So the relation R sub pi contains all pairs alpha beta such that there simply exists some gamma so that alpha beta gamma is a valid transcript. It makes the verifier accept. Okay, so this is a well-defined notion. And I claim first of all, I claim that this relation is sparse, meaning that for every alpha, there are few betas, very few betas, that are in the relation. Does anyone see why? No, so it actually doesn't have to do with H. I'm not saying anything about H yet. I'm just asking about this relation, which is not defined in a way that depends on H. I'm asking, so I'm claiming that for every alpha, there are very few betas so that there even exists a gamma such that alpha, beta, gamma is a valid transcript. So let me walk you through it. Let's assume otherwise, that there exists some alpha for which there are many betas for which there exists a corresponding gamma. So I will break the soundness of this interactive proof system, right? I will send alpha. Now I know that for most choices of beta, there exists a gamma. But we're talking about kind of statistical soundness. So I'll do a brute force search, looking for a suitable gamma. And once I'm guaranteed that one exists, I will find it, and I will break soundness. Okay, so really the soundness of this interactive proof guarantees that R sub pi is a sparse relation. Okay? Mm-hmm. Oh, so the way the relation is defined says that there exists some gamma that will make the verifier accept. In an interactive argument, there may well be a gamma, but the point is that it's hard to find it. The soundness of the argument only says that it's hard to find such gammas. Okay, here, once a gamma exists, then I don't care about running time. I will find it.
So the relation you defined before must be efficiently verified, right?
So which relation did I? Did I define a relation? Let's see. Okay, so it's a good question about what we want from R. So far, I haven't specified. Right? R is just, right now it's defined as a relation. I haven't said anything about its efficiency. And I'm just saying that if you look at this relation, and this relation happens to be, if I give you alpha beta, it's not clear that you can tell whether there exists a gamma or not. But I don't care. I'm just saying, let's stare at this relation. I'm claiming that it's sparse. For every alpha, yes, let's fix x not in the language. Sorry. So part of the description of the relation will be x, and I want to think of x not in the language. If one cares about adaptive soundness, then you can bake in x into the relation, but let's ignore that. Sorry, so I'm thinking of x being not in the language. Okay, so I have a relation, and I know that it's sparse. Yes, so sparsity is always like, think of the relation as like map between x's and y's. For every x, there should be very few y's in the relation. So in our case, for every alpha, very few betas, which exactly corresponds to soundness.
Alpha, beta, I should think of it as the statement here, right? Gamma is the...
No, so alpha is the first prover message, beta is the verifier message, and gamma is the second prover message.
The relation, yeah.
Right, okay, so for the relation, like alpha is the input, beta is the output. If you think of, a relation between inputs and outputs. Right, the relation is some, yeah, okay.
This soundness argument, how do you know it's defined alpha?
No, so I'm saying, so far, all I was saying is that for every, so I'm claiming that for every alpha, there are going to be very few betas in the relation. And if that's not true, if there exists some alpha, then I'm talking about, statistical soundness. So my prover who runs in infinite time can find alpha. Okay? So we see that the soundness guarantees that this relation is sparse. And the point is that if you have a cheating prover for this protocol, what does it mean? The cheating prover, given H, manages to find an alpha so that H of alpha, so that kind of alpha, we have a cheating prover, P star, who given H finds alpha star. And what do we know about this alpha star? If the cheating is successful, it means that for this alpha star, if you look at the beta star that you get from hashing alpha star, there is going to exist a gamma because he successfully cheats. Okay, so a cheating prover for the protocol on the right actually manages to find an alpha star, comma, H of alpha star, I'm ignoring X, that are in this relation. And that's exactly a violation of correlation intractability. We have this relation, we've managed to find some element in the input so that its hash, so that element together with its hash is in the relation. That is exactly what correlation intractability for this particular relation tells us should be hard to do. Okay, so far we've basically seen that correlation intractability for this relation, or rather this class of relations indexed by X not in the language, suffices for getting Fiat-Shamir. So our goal now is just to get a correlation intractable hash function. We're going to do it, for starters, for all relations. Okay, so with no further ado, I can introduce kind of our hash function, right, or hash function family. So each hash function, so we're going to be using our KDM secure encryption scheme. And kind of at first glance, it's going to look weird. And second glance, I think I'll try to justify why it's not so weird. So the hash function is going to be described by some ciphertext C. So each ciphertext defines a different hash function. And the messages that the hash function kind of expects to hash are going to correspond to encryption/decryption keys. We're talking about a symmetric key scheme, so encryption and decryption keys are the same. And it's defined very simply as follows. So the hash using C as a description of the hash function of the key K. I'm viewing the key of the encryption scheme as the message for my hash function, is simply to decrypt C using the key K. Okay, so kind of the role of the encryption key is as a message for the hash function. Kind of somewhat strange at first glance. And what we want to show is that this hash function is correlation intractable for all sparse relations. For purpose of simplicity for the talk today, let's kind of take things to the very extreme and just think of relations that kind of take sparsity to the limit. Basically, relations in which for every x, there's a unique y, so that xy is in the relation. And if you recall what the definition of a function is, as opposed to a relation, this is exactly a function. Right? So for every x, there's a unique y, such that xy is in the relation. And we want to show correlation intractability only for these kind of extremely sparse or maximally sparse relations. Okay, so this is the definition of our hash function. And here's a little bit of intuition of why we define things this way. Actually, it's not why we define things this way, but I think in retrospect, this is maybe a good explanation. So suppose that someone manages to break correlation intractability for some particular relation R that we care about using this hash function. So what does it mean? It means that given the description of a hash function, which is a ciphertext C, this adversary manages to produce an input to the hash family, to the hash function, which is K, so that, K comma H of K is in the relation. What this means, with using the definition of H, is that the decryption, K and C should be switched, but the decryption using key K of the ciphertext C is equal to R of K. In other words, or in some sense, it means that C is an encryption under key K of R of K. All right, so saying again, we have an adversary breaking the correlation intractability of this hash function, given a ciphertext C, manages to produce a key K so that C is an encryption of R of K under key K. And that looks a lot like kind of key-dependent message security, where we kind of, you're given an encryption of R of K under key K, and you're asked to recover K. So it looks quite similar, I would say, but kind of the order is wrong. Here we're saying first comes the ciphertext, and now you need to guess corresponding key, whereas in the KDM game, kind of first comes the key, you generate the ciphertext, and I ask you now to retrieve the key. And indeed, this is, this slight twist on the order of quantifiers is what causes our exponential loss in security. And I want to show that. Any questions? Okay, so I'll show you the analysis. This is going to be a quite technical slide, but it's just a single slide, so excuse me. After that, it'll be less technical. So let's see what happens. Yes. Yes. Right, exactly. So, right, and later we're going to leverage that. So the third paper in the list of papers is going to, and we're going to see it today, is going to leverage the fact that, for nice interactive proofs that we care about, we can say something meaningful about these relations. Yeah. Okay, so let's see the analysis. What does it mean that we have an adversary for correlation intractability for our hash function? So I'm going to have a list of experiments and events that I care about. The first one just corresponds to kind of correlation intractability game in which kind of, what is the experiment? I sample key K and generate a ciphertext C, which is an encryption of key of a random message, right? So random ciphertext C. Now I give my adversary, so this is kind of the experiment, the probabilistic experiment that I'm doing, or distribution that I'm generating, and I'm asking what is the probability if I give my adversary this ciphertext C, which was the hash function description. It outputs some key K star, and I'm asking what's the probability that this K star, comma, decryption sub K star of C is in R, is in this relation R. So that's exactly the definition of correlation intractability, and let's assume that this happens with probability at least epsilon. Okay, good. So this is just by assumption, and now I want to move to the next step. So here I was thinking of K stars kind of a fixed string, whatever the adversary outputs. Now I'm going to think of it as part of my experiment. So here I'm also sampling K star. So I'm using uppercase for random variables and lowercase for fixed things. So I'm going to sample K star by myself, and I'm asking what's the probability, kind of similar to before, but I'm insisting that the particular K star that the adversary outputs is the one that I chose ahead of time. Okay, so what are the chances of those? Very low, and indeed, I'm going to pay 2 to the lambda. Lambda is the length of the key, right? So I'm going to suffer a 2 to the lambda loss in my success probability, because think of my choosing the key K star after the fact, and I only have 2 to the minus lambda probability of hitting the specific one that he chose, because I chose the key at random. Okay, so this I hope this part is clear. Next step is where I'm going to use this universal ciphertext property, which says that it doesn't matter under which key I encrypt my message, I'm going to get the same distribution if I think of encrypting a random message. So now I've moved to, here in the previous slide, I encrypted C using the key K. Here I'm going to encrypt using the key K star that I just chose. And notice that the message M didn't appear anywhere before, so it's like I'm encrypting some M prime. By the universal ciphertext property, I can switch keys in this way. So now the experiment is I sample K star, I generate C as an encryption using K star, and I'm asking what's the probability that the adversary outputs K star so that K star satisfies the relation. Okay, so I don't have much room, so the next one should be probably the last one. So here's what's going to happen. So now I think of the experiment in which I sample K star as before. I fix M to be exactly equal to R of K star, and now encrypt C as before. And I'm asking what's the probability of A given C just outputting K star. To put it differently, you can think of this as the probability of A of C being equal to K star under the conditional probability where I sample a condition on M being equal to R of K star. So it's this conditional probability. Now just using the definition of conditional probability as kind of the conjunction of the two events divided by the probability for the second event, what I get is whatever I had before, this is exactly the conjunction of the events, divided by the probability over the conditional space. So what is the probability of M being equal to R of K star? And this exactly corresponds to the sparsity of the relation, right? If my relation is sparse, row sparse, then there's only row probability, or there is at least row, there's a most row probability. So I'm dividing by row, which makes this expression larger. Okay, so I suffered a 2 to the lambda loss, but I gained this kind of row factor, which boosts this back up again to something I'm going to show you that it boosts to something non-trivial. Okay, so this was the kind of super technical slide. I hope I didn't lose all of you. Right, so this is the sparsity of R. And, okay, actually, so let me say one more thing. So here we're thinking, of if I have an adversary that succeeds with non-negligible probability here over epsilon, and the sparsity is negligible, then overall I'm getting an adversary that succeeds in this KDM key recovery game with 1 over 2 to the lambda times 1 over negligible, which is more than polynomial over 2 to the lambda, which kind of contradicts optimal hardness. Okay, it's a mouthful. So that's how we got our this result using optimal KDM security, and we were shooting for correlation and tractability for all relations, and this was the cause of requiring unbounded KDM functions. How am I doing on time? I have some time. Okay, so let me tell you about the more recent work in which we managed to kind of significantly improve this aspect of needing to handle unbounded KDM functions. Okay, so we're going to shoot for only bounded KDM functions and do this for kind of nice interactive proofs. And the idea is very much in line with what Benny was suggesting. So the observation is that we need correlation and tractability for a specific class of relations. What relation of those are those? If we're thinking of the three-message interactive proofs, it's exactly the relation of, given alpha, alpha beta, does there exist a gamma? Okay, and the relevant efficiency of the KDM function for us would be what is the complexity given alpha to find a beta in the relation, right? So if okay. So that's what so if given alpha, it's easy to find a beta in the relation, I'm going to say that R is an efficient function. And now I want to ask two questions. First, are there really interesting interactive proofs in which, given alpha, you can find a beta that's in the relation for which there exists a gamma? Okay, this would mean that such handling these type of correlation of these type of relations would be interesting. And second, can we indeed get optimal KDM hardness with bounded KDM functions from kind of better assumptions that we know? And it turns out that the answer to both questions is positive. So first of all, are there interesting interactive proofs for which R is an efficient function? Turns out that, at least from my perspective, the two most interesting things to look at happen to have this property. So the first one is something that's called a delegation scheme, which I will define shortly. And the second thing is something that we've already seen, basically zero-knowledge proofs. So if you look at the classical Goldrake-Mikali-Wigderson protocol or the Hamiltonicity protocol that Alon showed yesterday, those happen to have, in a particular sense that we're going to see, they will have this efficiency property, that given the message alpha, you can find a beta for which there exists a gamma. We're going to see that. Yes? No, so the soundness says that for every alpha, most betas should be bad. You're going to reject. And I'm asking, forget about a random beta. Can you find efficiently a beta which is bad for you? See the difference? So soundness says that. Right, but I'm asking like the sparsity or what soundness implies is that for every alpha, most of the betas are going to not be in the relation. But I'm asking, I give you alpha, can you find, a random beta is not going to do, but can you find some weird beta for which it will be in the relation? That's what I'm asking. Okay? Right, so I know that so in particular, just sampling a random beta won't do. But is there a clever way for every particular alpha to find beta for which there exists a gamma? That's the efficiency notion that I care about. Okay, so I'm claiming that for these two classes of interactive proofs, they have this property in some sense. We'll see. And for the second question, can we get kind of the KDM security for bounded KDM functions? As Benny was hinting, this is something that we can do, but not quite with optimal hardness. So the results starting with the work of Bonet and Benny and others, but they don't get optimal hardness. We're going to need to work a little bit more and assume stronger assumptions. Okay, so let me tell you a little bit about what are delegation schemes and what we can get. I have until 3:45, right? Okay. So what is publicly verifiable non-interactive delegation? So it's very similar to argument systems that we've already seen, but the point is that I really want to insist on efficiency and focus less on zero knowledge. Right, so the setup that I have is that I have a weak computational device, this weak laptop, talking to the cloud that it does not trust, and the laptop wants to verify that X belongs to L. Doing it by yourself takes n to the 17. That was Alon's favorite example. And I would like the laptop to be much faster, maybe run in time n squared or even just linear in n, the input size. Right? And the hope is that I can do this non-interactively. So there's going to be some short CRS that everyone sees, and the cloud just sends a tiny, tiny proof and convinces our laptop. Okay, so what is known about this publicly verifiable delegation? So PV is publicly verifiable, meaning that it's just a public CRS. So it's known under knowledge assumptions. I believe that Jens will talk about this on Thursday. It's known, of course, in the random oracle model. I guess we haven't seen Ellie may talk about it on Thursday. We know this using indistinguishability obfuscation, which is a very strong assumption. And we know this under this notion of zero testable homomorphic encryption, for which we don't have any good concrete candidates. So this is kind of open to get this notion of publicly verifiable delegation. I should mention that there's a concurrent work of Kalai, Paneth, and Lisa Yang, who also construct a publicly verifiable delegation scheme. They do this from a new but falsifiable assumption on groups that have a bilinear map. Okay, a downside of their work is that their common reference string is both long and a reference string rather than a random string. Although there are rumors that they managed to shorten the length of the CRS. I'm almost positive that it is still a common reference string rather than a random string. No, but the point, so the results I'm talking here are for kind of deterministic computations. Okay? Okay, so what do we show? Well, so the assumption that we have is optimal hardness of kind of key recovery attacks on FHE schemes. And for the statement of this result, we don't have to say anything about KDM. So just assume optimal hardness of key recovery for any of the known FHE schemes that we have based on lattices. But here I'm kind of thinking of the full-fledged FHE schemes to those who are experts in the crowd after bootstrapping. But anyhow, this is the assumption. And under the assumption, we show that any language that you can, in NC, meaning computable by kind of shallow circuits or in fast parallel time, has a publicly verifiable non-interactive argument system where the verifier runs in almost linear time and the prover runs in polynomial time. So this is the first kind of corollary that we get from Fiat-Shamir, or from our implementation of Fiat-Shamir. The way that we do this, I want to say, I will say a little bit more of how we do this and then end. So the way our approach for doing this is by applying Fiat-Shamir to a protocol of Goldwasser, Kalai, and Guy Rothblum, so GKR, which it's a very efficient, actually being implemented protocol. Its main downside is that it's highly interactive. It requires something for NC, some polylog number of rounds of back and forth interaction. And when we come to apply Fiat-Shamir here, we face two challenges. The first is that we need to show that for this particular interactive proof, the relation R that we get, from alpha finding beta is something that you can do efficiently. So that is one challenge that we need to show. The second is, this protocol, as I said, takes a super constant number of rounds. We've already seen that Fiat-Shamir in the morning session, we saw that Fiat-Shamir for a protocol with super constant number of rounds just fails even in the random oracle model. Forget about a concrete hash function. So this seems disturbing. Okay, so we have a protocol that's not constant round. How can we apply this? And actually, because I don't want to get too much into the details of the protocol, I won't show you that this relation R is efficient in GKR. So you'll either need to take my word for it or ask me offline. I'll be happy to tell you more. But I want to tell you a little bit about how we avoid this trap of constant round or get away from this barrier of Fiat-Shamir not working generically for all constant round interactive proofs, because I think there's a nice idea going on there. Okay, so we're trying to apply Fiat-Shamir for a protocol that has a super constant number of rounds. And the first thing that we can do is, go a couple of years to the past to work by Ben Sasson, Chiesa, and Spooner, who show that actually Fiat-Shamir is secure for multi-round protocols if this protocol satisfies a stronger notion of soundness. So not only should it be, statistically sound against a computationally unbounded cheating prover, I'm going to give the cheating prover even more power, or they give the cheating prover more power, basically the power of rewinding. So the prover can start interacting with the verifier, but at any point in the protocol, it can say, oops, I want to go back. And it's allowed to do so, let's say, a polynomial number of times. And BCS show that Fiat-Shamir is secure if you apply it to such protocols in the random oracle model. This doesn't mean that it's still going to be secure when you use correlation intractable hash functions rather than the random oracle model. And as a matter of fact, that remains open. So this is something that we tried but failed to show, that correlation intractability, this property by itself, suffices for instantiating Fiat-Shamir for resettably sound proofs. It's something that sounds believable, we were unable to show it. Proofs. Everything I'm talking now is proofs. Why are you, what is the concern? Are you wondering? So interactive proofs are a special case of IOPs. Right? IOPs just have these long messages. But everything is statistical.
And there are no longer proofs of knowledge, right?
So what are not proofs of knowledge?
Because you're resettable, your interactive proof is no longer a proof of knowledge. If it's resettable, then how would it be different from a knowledge extractor, which extracts knowledge by reminding?
So if you have the extractor, then the proof is relatively weak.
But then it's no longer zero knowledge.
So maybe I'll take it offline. I'm not sure what the answer is. One thing to note is that here we're talking about a bounded number of rewinds. Okay, so that potentially the knowledge extractor can rewind even more. Okay? Okay, so we're not able to show that resettable soundness suffices, so we're going to shoot for an even stronger notion of soundness, and that notion will suffice, again, for implementing Fiat-Shamir using correlation intractable hash functions. And the notion that we consider, we call it round-by-round soundness, and it's the following. So again, we're talking about a statistical notion or information theoretic notion. So we say that a protocol pi has round-by-round soundness if the following holds. So I'm going to assume that there's some predicate. The predicate takes as input kind of partial transcripts of the protocol and outputs a bit, yes or no. And the property that I wanted to have is that if you apply this predicate to the empty transcript, then the predicate says 0, and I'm going to think of 0 as being doomed. Okay, we'll see in a second why I think of it as doomed. And I want to have the property that for any kind of partial transcript that is doomed, the predicate is 0 on it. If you try to continue it using kind of a random message from the verifier, with very high probability you're going to stay doomed. Okay, that's property 2. And then the third thing is that if you look at a full transcript, it kind of corresponds to when the verifier rejects. So if the transcript is doomed, the verifier is going to reject. So kind of here's how you should think of it. You start the protocol, X is not in the language. You begin, and you're in a doomed state. Now the prover sends a message. So the prover sends a message, you're in a doomed state. Now the verifier tosses some coins. I'm saying with overwhelming probability, you remain in the doomed state. And then you continue. So again, the verifier tosses more coins, doomed, 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 all the way to the end. And then at the end, the verifier can check that you're doomed and is going to reject. So that's what round-by-round soundness means. And as an aside, turns out that if you take any interactive proof having regular soundness and apply parallel repetition, you're going to magically get this more stronger notion of round-by-round soundness. Okay, so we can take any interactive proof and make it satisfy this notion. And I want to kind of, for the last part of the talk, I want to quickly show you that round-by-round soundness together with correlation intractability suffices for Fiat-Shamir. So here's how it goes. Let's suppose that we have a protocol. We start with a multi-round protocol that has round-by-round soundness. And I'm going to define my predicate as, or my relation that I care about as follows. Again, this relation is kind of indexed by X, not in the language. So the relation consists of partial transcript. So the input to the relation is a partial transcript tau, and the output is a next verifier message. And the pair is in the relation if tau is a doomed transcript, but if you concatenate beta, it turns into a non-doomed transcript. And just by the definition of round-by-round soundness, I claim that this relation is sparse. Right? We know that for every partial transcript tau, with overwhelming probability over the choice of beta, you're going to stay doomed. Okay, so for every tau, and most betas, tau beta is not in the relation. Okay. But I claim that if you manage to break round-by-round soundness of the interactive proof, then you've broken correlation intractability of the relation. Why? Okay, I guess I don't have information about it. But the idea is that if you've managed to break soundness, then it means that you start off, the empty transcript was doomed, but the full transcript that you've provided is not doomed because the verifier accepts it. So there must be some point in the middle where you've switched from doomed to not doomed, and that point that you found is something that breaks the correlation intractability for this relation. Okay. Right, so I won't have time to talk about how we can apply this to the GMW or Blum interactive proofs, but with an extra idea, you can do this too. Right, and then you get, what we got was NIZKs from search LWEs. When I gave this talk a couple of months ago, I said that NIZK from LWE is a wide open problem, and there was a $100 cash reward, which is now gone. Sorry. Okay, so I'm going to skip over GMW. And skip over how we managed to get kind of this optimal bounded KDM security. And go to the summary. So what I tried to show you today is kind of in a very fast pace, that Fiat-Shamir for proofs actually can be realized using strong assumptions, which in these follow-up works have kind of vastly improved. And I think it's kind of remarkable how the assumptions have improved from sub-exponential IO plus optimal obfuscation just 2 years ago to LWE now, which is nice. And a really interesting open problem, I think, is random oracles are useful beyond just Fiat-Shamir, and I'm curious whether these techniques can be used to get other random oracle-like properties using concrete hash functions. And I'll end here.